welcome back to our channel and welcome to another episode of Crash Course 126! So I'm Angela and I'm going to discuss about the basics and the concept of reptilian and their three-chambered hearts.
I'm Bea and today I'm going to discuss a scientific paper about the topic that Angela is going to discuss for us first.
So sit down, take down notes, and enjoy the ride as we delve into the reptilian heart.
Except for alligators and crocodiles, all reptiles have a three-chambered heart. This heart is made up of two atria and one ventricle.
So how does the heart work? Basically, the mechanism is similar to that of the mammalian circulatory system. The only difference is in the ventricle area, as reptiles have only one. In a reptile, the oxygenated blood returning from the body tissues enters the right atrium. It passes this blood into the ventricle, from where it is pumped to the lungs for oxygenation. The oxygenated blood from the lungs returns to the left atrium and once again enters the same ventricle from which it is pumped to the body tissues. Even in the three-chambered heart, however, as recent research has shown, in contrast to earlier beliefs, there is a little mixing of oxygenated and deoxygenated blood. This has been achieved by the development within the ventricle of interconnected subchambers within which a sequence of changes in blood pressure takes place. Several anatomical variations occur among the reptiles, but a simplified description of the lizard heart will serve to illustrate one way in which this circulatory efficiency was accomplished. The ventricle of the lizard heart is incompletely partitioned into two subchambers by a muscular ridge that descends from the roof of the heart almost to the floor. The right subchamber is called the right ventricle or cavum pulmonale. It leads to the lungs. The left subchamber is called the left ventricle or cavum venosum. It receives blood from the right atrium and leads to the body. The two subchambers are connected not only beneath the partition but also across its incomplete rear. A third subchamber called the cavum arteriosum is situated in the upper wall of the right ventricle. It receives blood from the left atrium and is connected through a valve-controlled opening to the left ventricle. When the two atria contract, oxygenated blood from the left atrium enters the third subchamber or cavum arteriosum, pressing against and shutting the valves, controlling the opening into the left ventricle. This closes off the cavum arteriosum and temporarily holds its contained blood in storage. At the same time, the deoxygenated blood in the right atrium has been pumped into the left ventricle, filling it to overflowing with the excess blood moving across the open posterior end of the muscular partition into the cavum pulmonale. The three ventricular subchambers are now filled with blood, with oxygenated blood in the cavum arteriosum and deoxygenated blood in the other two ventricles. Resistance in blood flow is lower in the pulmonary circuit than in the systemic circuit, so that when the ventricles contract, the deoxygenated blood in the right ventricle follows the path of least resistance and proceeds through the pulmonary artery into the lungs. The emptying of the right ventricle causes more deoxygenated blood from the left ventricle to move around the open end of the partition into the right ventricle and to continue on to the lungs. The contraction of the ventricle also brings the partitioning muscular ridge into full contact with the floor of the heart, sealing off any flow from the right ventricle back into the left ventricle. As the ventricles continue their contraction, the pressure and the blood held within the third cavum arteriosum exerts a reverse force on the valves, opening the passageway between the cavum arteriosum and the left ventricle. The oxygenated blood in the third subchamber now moves into the left ventricle and from there into the aortas, leading to the body circulation.
So we have here a commentary paper by Jensen et al. With its title, How the Python Heart Separates Pulmonary and Systemic Blood Pressure and Blood Flows. So before anything else, let us delve into the anatomy of the heart of P. molurus or the python. Now let's look at the internal dorsal view. We can see the atria near the base and the ventricle near the apex. The single elongated ventricle is then divided into two major chambers. You can see the cavum pulmonale or the pulmonary chamber indicated as CP and the cavum arteriosum or the systemic chamber indicated as CA. and the cavum venosum, indicated as CV, situated between the two. The cavum venosum is a shallow chamber, but equally as important because blood entering the pulmonary chamber during diastole passes through it, and the blood that will go through the systemic chamber must traverse the cavum venosum to reach the aortic arches. The vertical septum indicated in the arrows runs from the apex approximately 3/4 of the length towards the base of the ventricle, and thereby completely partitions the caudal part of the ventricle into a right and then into a left side. Two other important septa are the muscular ridge MR and the bulbous lamel BL, which divides the base of the ventricle during ventricular contraction. So now, let's discuss the flow and pressure separation in the heart. Previous studies investigated how blood flows through a python's heart using physiological saline solution, and they found out that oxygenated blood entering the cavum arteriosum was ejected into the systemic arches, while deoxygenated blood from the right atrium was directed toward the pulmonary circulation or the pulmonary or through the pulmonary chambers. These findings suggest that the heart is functionally divided during the filling and the ejection of blood. So based on these graphs, the systemic side, or the left side of the ventricle, generates higher pressures from the right. So the difference in pressure allows the motion of blood in the heart. So now let's discuss how the python heart separates blood flow during ventricle contraction. So here, we have an image generated from an endoscopy showing the pulmonary chamber of the python heart. So during diastole or ventricle relaxation, blood flows through the opening between the crest of the muscular ridge, which is indicated here as MR, and the bulbous lamelle, which is indicated as the BL. And the valves of the pulmonary artery, or the VAP, are closed. On the other hand, during systole or ventricle contraction, the bulbous lamelle abuts the muscular ridge, which separates the pulmonary chamber from the rest of the ventricle during contraction. Therefore, the difference in ventricular pressure can be attributed to the abutting of the bulbous lamelle towards the muscular ridge, which separates the pulmonary chamber from the rest of the ventricle, which then generates a lower pressure in the pulmonary chamber. This relates to the importance of a pressure difference on the flow of blood discussed earlier. So in previous studies, it was even shown that pythons with poorly developed muscular ridges weren't able to exhibit ventricle pressure separation. So now let's discuss how the python heart separates blood flows during ventricular filling or ventricular relaxation. So during ventricular filling, atrioventricular valves are forced caudally towards the muscular ridge and the vertical septum during ventricular filling, which would effectively guide the oxygen-poor blood from the right atrium into the cavum pulmonale or the pulmonary chamber, while oxygen-rich blood is directed from the left atrium into the cavum arteriosum without any backflow of blood. So lastly, let's discuss cardiac shunts in the python heart. So this is where the cavum venosum is of utmost importance. It is worth noting that the functional size of cavum venosum and the interventricular canal during diastole in pythons are reduced. As discussed earlier, oxygenated blood and deoxygenated blood both pass through the cavum venosum. So this makes the mixing of blood inevitable. Thus, when the bulbous lamelle and the muscular ridge separate the cavum venosum and the cavum pulmonale during systole, the residual venous blood or the deoxygenated blood in the cavum venosum, it is washed out along with the arterial blood from the cavum arteriosum into the aorta. So due to the small sizes of cavum venosum and the interventricular canal, the residual volume is always small and negligible, and it only constitutes a very small portion of the cardiac output. That was our video on the reptilian heart and its 3 chambers. So we hope you liked our video. We hope you learned a lot. And then don't forget to
Like and subscribe.
don't forget to click the bell to be updated on future uploads.